Welcome back, Calculus 3 fans. In this video, a discussion of sequences. So just as an overview, we'll talk about some of the basics. We'll review a topic from Calculus 1 called the squeeze theorem, and then we'll briefly talk about a property of sequences called monotone. So first in basics, as we mentioned last time, one of the things that we'll like to do is identify a formula for a given sequence. That's not so hard to do. In this case, we see the first term of the sequence is 1, the second term of the sequence is 2, and so on and so forth. Therefore, we'll go ahead and define the nth term in the sequence, a sub n, as just n. It's common to represent sequences with these curly braces, so the curly brace n from n equals 1 to infinity, or simply just curly brace n, both work. Similarly here, we see the first term of the sequence is 2, the second term of the sequence is 4, the third term of the sequence is 6, and the fourth term of the sequence is 8. Pretty clear that we have the even numbers. In this case, those even numbers are, of course, represented by a sub n equals 2n. So the sequence in this case will just express as curly brace a sub n, where that is 2n. In the third example, we have the odd numbers with one new wrinkle here, the sign flopper. Now there are some different ways to represent the sign flopper. The easiest way to represent the sign flopper is with a power of -1. So in this case, we'll go ahead and take our sequence to be -1 to the n plus 1 times 2n minus 1. And if you aren't sure, you can always write out a few terms just to check, right? So in this case, that would be something like -1 squared times 2 times 1 minus 1, and -1 to the third times 2 times 2 minus 1, and so forth. And you can see that we definitely get the right answer there. So 1, 3, -3, 5, and -7, and so forth. Just a quick observation here. Observe that -1 to the n also sign flops. Now, one interesting thing about these three sequences is that none of them converge, right? You can see they all get arbitrarily large as n goes to infinity. Something we're certainly interested in is determining whether a sequence converges, and an easy way to do that is to use our friend the limit from Calculus 1. So here is an overview of that. If f is a continuous function that matches the sequence for all integer values of n, and f has a limit as x tends to infinity, then the sequence a sub n converges as n goes to infinity. So you might be wondering here why we use x instead of n. It turns out that in sequences n is typically a positive integer, whereas x is a real number, and all the calculus we do works on real numbers. So we can go ahead and use our tricks from Calc 1 to indicate convergence of sequences as long as they match everywhere. Okay, so here's an example, the sequence containing terms n over n plus 1. So just to get an idea of what's going on here, I think you'll agree that when n is 1, we get 1/2, 2/3, 3/4, and so on and so forth. And here, we'll go ahead and define the function to be x over x plus 1. And you can use your favorite method to show that this limit as x goes to infinity of x over x plus 1 is 1. So this is how we know that a sub n, which is n over n plus 1, converges and the limit is 1. Okay, it's similar but not quite so simple for this next example, in which we have the sign flopper out front times minus 1 to the n plus 1 times n over n plus 1. Okay, so just to get an idea of what's happening here, we'll go ahead and write out a few terms again. So it's going to be 1/2 and negative 2/3, 3/4, negative 5/6, and so on and so forth. Now, certainly we know what happens to part of this sequence, right? We know that n over n plus 1 goes to 1 as n goes to infinity. Now that tells us that as n gets really large, the sign flopper term has sort of this annoying effect that if we start writing out the terms, this will go to plus or minus 1, depending on whether n is even or odd. Okay, so we can see then that this sequence does not converge. It doesn't close in on a single number, so we would say that this is an example of a divergent sequence. Okay, finally a third example, the example where the nth term in the sequence is n times e to the minus n. So here is an example where our calculus 1 definitely comes in handy. So we'll take our function f of x to be x times e to the minus x, which we can express as x over e to the x. And then we know that the limit as n goes to, as x goes to infinity, of this function x over e to the x by the beauty of L'Hopital's rule is 0. Okay, so we can say that our sequence converges with limit 0. Okay, and once again, this is an example of an operation that we would not be able to do if we didn't have a continuous function, right? Because you can't take derivatives technically with functions that aren't continuous, so you can't use L'Hopital's rule in that case either. Okay, a quick discussion of the squeeze theorem. You'll remember the squeeze theorem from Calc 1 as a strategy to tell you the limit of a function when that function is bounded between two other functions whose limit you know and are the same. So it's the same thing here for sequences. If we have a sequence b sub n, which is bounded between a sub n and c sub n, and a sub n and c sub n both converge to L, then b sub n does too. As a special case of the squeeze theorem, I was getting a little ahead of myself before. We know that the sequence a sub n is always bounded between its absolute value and its negative absolute value. So if the absolute value approaches 0, then a sub n does too. So here's an example of use of the squeeze theorem for this sequence where the nth term a sub n is given by n factorial over n to the power n. And just a quick reminder about the factorial. N factorial means you start with n and multiply all of the integers below it. So in this case, terms in the sequence, of course, start at 1, and then the second term is 2 times 1 divided by 2 times 2. The third term is 3 times 2 times 1 divided by 3 times 3 times 3, and so on and so forth. N factorial divided by n to the power n. So here we'll point out that that this sequence actually has a bound. And to see that, we'll go ahead and have a look at the nth term. So the nth term here, I've written our factorial kind of in reverse order. It has form 1 times 2 times 3 times 4 all the way to n. divided by n times n times n all the way n times. So we can see that this is definitely equal to 1 over n times a fraction that looks like 2 times 3 times 4 all the way to n divided by n times n times n all the way to n. And this thing we know is less than or equal to 1. So our nth term, therefore, is less than or equal to 1 over n. Now, certainly we know something about 1 over n. 1 over n converges, and our nth term here is bounded between 0 and 1 over n. So we know that this sequence converges and is limited to 0 by the squeeze theorem. Okay, last thing to discuss here is the concept of a monotone sequence. And sort of the overview for monotone sequences is that a sequence that's monotone, that is, it's only going in one direction, either monotone increasing or monotone decreasing, and bounded, that means not going up to infinity, has to be convergent. So if it's only going in one direction and it never goes off to infinity, we know that these sequences are convergent. So an important question is to be able to determine when a sequence is monotone, and we can determine when a sequence is monotone in a few different ways. One is if the n plus first term minus the nth term is positive, right? So this would be monotone increasing. Similarly, if the ratio of the terms is bigger than 1, that tells us that the n plus first term is bigger than the nth term. Or similarly, if we can come up with a function whose derivative is positive, then we know that that sequence is increasing too. So again, this is a discussion here of monotone increasing, and it's similar for monotone decreasing, just change the inequalities in each of those statements. So here's an example of a sequence we've looked at before. This is a sequence where the nth term is given by n over n plus 1. And we can see that this is monotone increasing in a few different ways. So we'll go ahead and just run through those individually. So for instance, the difference in the n plus first term and the nth term is given here by n plus 1 over n plus 2 minus n over n plus 1. Now, it's not hard to run through a little bit of algebra and show that this is equal to 1 over n plus 1 times n plus 2, which is certainly a positive number. So we can see that this term is increasing. The sequence is increasing. Similarly, if we have a look at ratio of nth term to n plus first term, a little bit of algebra can show us that this is equal to the following expression. The expression is n squared plus 2n plus 1 over n squared plus 2n, which we can simplify to 1 plus a quantity that's positive. So this is certainly greater than 1, which also tells us that the sequence is increasing. Finally, if we define a function f on the continuous variable x, again here so we can use calculus such that it matches our sequence at any point. In this case, I'll write it as x over x plus 1. Then, with a little bit of work using the quotient rule, you can pretty quickly show what the derivative is. That derivative turns out to be 1 over x plus 1 quantity squared, which is definitely a positive number, and we know if a derivative is positive, then the function is increasing. Okay, so 3 different ways to show that this sequence is increasing, monotone increasing. So last example from this section, we're going to go ahead and show that the sequence of numbers a sub n, where a sub n is given by x to the power n in absolute value over n factorial, is a convergent sequence no matter what the number x is. Okay, so we'll start off here with x equal to 0. Of course, if x is 0, then a sub n is 0 for all n values n, and we can see pretty quickly that this converges. Now, in the case where x is not a 0 number, we can see that the ratio of the n plus first term to the nth term is given by this expression, which we can pretty quickly simplify. Just look at the reciprocal of the denominator here and regroup things carefully. And of course, if there are n plus 1 x's in the numerator and n in the denominator, we're left with 1 x in the numerator. And n factorial over n plus 1 factorial. Notice that n plus 1 factorial can be written as n plus 1 times n factorial. So those cancel, and we're left with n plus 1 in the denominator. Now this, as it turns out, is less than 1 as long as n is big enough. So this is something we categorize as eventually decreasing, but it's decreasing, telling us that our sequence is monotone. Now our sequence is monotone decreasing, and it's also bounded below. So it's always going down, and it's always greater than 0. So we know then that a sub n has to be convergent. Okay, hope you've enjoyed these examples on sequences and determining whether they're convergent, and we'll see you next time.